Good morning. In the earlier lecture, we talked about interpretation of curl of a vector. It needed 2 lectures. We have completed this in the previous lecture. Let us go to the next article, and the next article is about Laplacian operator. Our next article, Laplacian operator. To get Laplacian operator, Laplace is the name of the physicist who devised this operator, and so in his honor we call this operator as Laplacian operator. To get Laplacian operator, we have to make use of the 3-dimensional vector differential operator del or nabla, and we are familiar with this. The vector differential operator del or nabla is equal to, as you know, I dou by dou x j dou by dou y plus k dou by dou z. Vector differential operator nabla or del is this. Del or nabla is equal to I dou by dou x plus j dou by dou y plus k dou by dou z. The Laplacian operator is obtained if we take dot product of 2 vector differential operators del dot del, and this del dot del is written as del square. Del dot del is written as del square, and this del square is equal to, for this del use this bracket and write it here, del dot del is equal to del square is equal to, in the first bracket value of this del dot is here, remember it is a dot product. In the second bracket value of this del and this del is same. We are taking dot product of 2 nablas, 2 dels. So, I have to write del dot del is equal to del square is equal to this bracket dot this bracket. Let us take dot product of this. First dot product of this with these 3 terms, then dot product of this second term with these 3 terms, and then dot product of the third term with these 3 terms, and that is equal to dou x dou 2 by dou x square I dot I plus dou by dou x dou by dou y I dot z. dou by dou x dou by dou z I dot k plus dou x of this with these three terms. So dou by dou y of dou by dou x z dot I plus dou by of this with this, that is just dou 2 by dou y square z dot z plus dou by dou y of dou by dou z z dot k, and the last term is dou by dou z of dou by dou x k dot I plus dou by dou z of dou by dou y k dot z plus dou 2 by dou z square k dot k. Dot product of this with this is dou 2 by dou x square I dot I plus dot product of this with this is dou by dou x of dou by dou y I dot j plus this with the last term is dou by dou x of dou by dou z I dot k. Similarly, of second with these three terms is dou by dou y of dou by dou x j dot I plus dou 2 by dou y square j dot j plus dou by dou y of dou by dou z j dot k plus dou by dou z of dou by dou x k dot I plus dou by dou z of dou by dou y k dot j plus dou 2 by dou z square, it is not x. Dou 2 by dou z square k dot k, and you know the rules of dot product of rectangular unit vectors I dot I 1 j dot j 1 k dot k 1. So value of this is 1, value of this is 1, value of this is 1, value of this is 0 0 0 0 0 0. Value of this dot product and this dot product is 1. Value of remaining dot products, this one, this and this is 0. So out of these 9 terms, 6 terms will become 0, only 3 terms will survive. Let us collect the terms which survive, and 0 terms will be just ignored, because 0 plus anything is anything. 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3. No need to consider 0 when we are doing the summation. So just ignore the 0 terms and collect the remaining one. When you collect the remaining terms, this Laplacian operator ignoring zero terms, collecting the terms which survived, this term and this term, we got Laplacian operator del square is equal to del dot del is equal to dou 2 by dou x square plus dou 2 by dou y square plus dou 2 by dou z square. Equation 1. This is known as Laplacian operator. Equation 1 is known as Laplacian operator. Have a look inside the expression for Laplacian operator. What we find? We find that it is dot product of two vectors, and dot product of two vectors is a scalar. It means that del square is a scalar. This is a scalar. That is, Laplacian operator is a scalar operator. It is not vector differential operator. Laplacian operator is not vector differential operator. It is scalar operator. One thing, it is operated on scalars. Laplacian operator, which is a scalar, operated on scalars, and the result is also a scalar. Let us consider a scalar function phi is equal to phi of xyz. Phi is equal to phi of xyz. Then del square phi will be del square phi will be equal to dou 2 phi by dou x square plus dou 2 phi by dou y square plus dou 2 phi by dou z square. Equation number 2. Scalar point function phi is equal to phi of x, y, z. Okay, and when Laplacian operator del square is operated on this scalar point function, what you got is del square phi is equal to dou 2 phi by dou x square plus dou 2 phi by dou y square plus dou 2 phi by dou z square. Phi is differentiated 2 times with respect to x. Phi is differentiated 2 times with respect to y. Phi is differentiated 2 times with respect to z, because phi is a vector point function which is a function of the point represented or specified by coordinates x, y, z. So, what you see here, the operator del square, Laplacian operator, is a scalar. It is operated on a scalar, and the result itself is a scalar. So, this operator del square, which is given by del dot del, we found here. We derived expression for it. This operator is known as Laplacian operator. It's so simple. Hope you got it. In the next lecture, we shall go for the next article. Thank you.